Then we have here 100 samples mean, all of them sample of size 5. This is the sample number 100. In the other slide, we have 100 samples, more, 100, additional 100 samples, all of them of size 5. Actually, we want to know how is the distribution of these, all of these 200 samples mean. We want to know what is the mean of all of these samples mean. Let's use this Greek letter. 200 is not the population, but let's use this symbol to, but the correct symbol is the mean of all samples mean. That should be the true symbol. How can we obtain this mean? We need to add all of these samples mean and divide it by the total. The total is 200. And the standard deviation of all samples mean, that is the population. And actually here, we should use this sample, standard deviations for this sample of 200. But let's assume that this is a population is equal the square root of the sum of all variation of all samples mean respect to the mean of the population square divided by n, because is the population. Let's assume that this is a population. When we compute this formula and this formula of all of these 200 samples mean, we obtain that the mean of all 200 samples mean is 2.46, which is the same as the mean of the population. And the standard deviation of the samples mean is 0.0086, which is smaller than the standard deviation of the population. In the next slide, we are going to show the histogram of these 200 samples mean. All of them sample size is 5. And the shape, the theoretical curve that describes this distribution will be mound shape. We have here only 200 samples. All of them sample size is equal 5. But if we obtain all possible sample size 5, all possible, not 200, but all of them, we can obtain this distribution. This is a theoretical distribution for all of them. Let's analyze in this slide, what is the impact of the sample size in a sampling variability? Actually, what is the best measurement of variability for a data that is quantitative? The best measurement of variability for data that is quantitative is the standard deviation. Then we expect that when my sample size increases, the variability of all samples mean should be smaller. It's implied that the standard deviation is smaller. Then in this case, instead 5, my sample size will be 20. And we are going to obtain all 200 sample size 20 from the same population. The mean is 2.46 and the standard deviation is 0.02 grams. Then that is the histogram for 200 samples size 20. And the theoretical curve is also normal. If we obtain all possible samples, not 200 samples, all of them, the theoretical distribution for these 200 samples will be normally distributed. But in this distribution, the mean is the same as the population, 2.46, that is the mean of the population, but the standard deviation is 0.00045. Actually, this standard deviation is smaller than this when the sample was 5. And actually is smaller than 0.02 when the sample is 1. As we expected, there is a less variability in the distribution of the sample's mean with n equal 20 than with n equal 5. Then what is the role of the sample size? Actually, the population, when we observe the distribution for individual value, when the sample size is 1, and when the sample size is 5, and when the sample size is 20, the standard, the mean in all of these cases will be 2.46, 2.46, 2.46. It's the same mean. The center of all of these three different distributions, the center is the mean of the population. However, the standard deviation, the variability of all value, when the value are individual, is this value. But when we increase a little bit the sample size to 5, the variability will be smaller than this one. And when we increase the sample size to 20, the variability will be, or the standard deviation will be smaller than this and obviously smaller than this one. And the bigger is the sample size, the smaller will be the standard deviation, the variability of this distribution. As the sample size of the sample increases, the standard deviation of the distribution of the sample means decreases.